Hello friends, welcome to KHC's audio. In this audio, we are going to see the chapter 3rd of standard 9, that is atom and molecule. Let's start this chapter. Ancient Indian and Greek philosophers have always wondered about the unknown and unseen form of matter. The idea of divisibility of matter was considered long back in India around 500 BC. An Indian philosopher, Maharishi Kanath, postulated that if we go on dividing matter, in India the matter is known as the padarth. We shall get smaller and smaller particle. Ultimately, a time will comes when we shall come across the smallest particle beyond the further division will not be possible. He named this particle Parmanu. Another Indian philosopher, Pakudha Katyama, elaborated this doctrine and said that this particle normally exists in a combined form which gives various form of matter. Around the same era, ancient Greek philosopher Democritus and Leucippus suggested that if we go dividing matter, a stage will come when particles often cannot be further divided further. Democritus called the indivisible particle atom. The meaning of atom is indivisible. All this was based on the philosophical consideration and not much experimental work. To validate these ideas could be done till 18th century. By the end of 18th century, scientists recognized this difference between element and compound and naturally become interested in finding out how and why element combine and what happen when they combine. Antoine and Lavoisier laid the foundation of chemical science by establishing two important laws of chemical combination. Let's start the what are the laws of chemical combination which are founded by and established by the Antoine and Lavoisier. Let's start. There are two laws of chemical combination were established after much experimental by Lavoisier and the Joppes and Proust. The first law is law of conservation of mass. In there, a change in mass when a chemical charge take place. Let us see an activity to explain it better way. Take one of the following sets X and Y of chemical. In X sets, the compound or the chemical is copper sulfate, barium chloride, lead nitrate, and in the Y set, sodium carbonate, sodium sulfate, sodium chloride. Prepare separately 5% solution of any pair of substance listed under X and Y in water. Take a little amount of solution of Y in a conical flask and some solution of X in the ignition tube. Hang the ignition tube in the flask. Carefully see that the solution do not get mixed. Put a cork on flask. You can able to see the how the experiment is in your screen. Weight the flask with the content carefully. Now tilt a spiral the flask so that the solution X and Y get mixed. Wait again. What happened in the reaction flask? Do you think that chemical reaction has taken place? Why should we put a cork on the mouth of the flask? Does the mass of the flask and its content change? Then, the law of conservation of mass states that the mass can neither be created nor destroyed in chemical reaction. After that, let's start the second law of chemical combination, that is law of constant proportion. Lavoisier along with other scientists noted that many compounds were composed of two or more elements and each such compound had the same element in the same proportion irrespective of where this compound came from, who prepared it. In compounds such as water, the ratio of the mass of hydrogen to the mass of oxygen is always 1:8. Whatever the source of water, thus if 9 gram of water decomposed 1 gram of hydrogen and 8 gram of oxygen are always obtained. Similarly, in ammonia, nitrogen and hydrogen are always present in the ratio 14:3 by the mass, whatever the method or the source from which it obtained. This leads to the law of constant proportion, which is also known as the law of definite proportion. This law was stated by Proust as in a chemical substance, the elements are always present in definite proportion by mass. The next problem faced by the scientist was the given appropriate explanation of this law. British chemist John Dalton provided the basic theory about the nature of matter. Dalton picked up the idea of divisibility of matter, which was still then just a philosophy. He took the name atom as given by the Greek and said that the smallest particle of the matter are atom. His theory was based on the law of chemical combination. Dalton's atomic theory provides the explanation for the law of conservation of mass and the law of definite proportion. Let us know about who is John Dalton. John Dalton was born in a poor weaver's family in 1766 in England. He began his career as a teacher at the age of the 12. 7 years later, he became a school principal. In 1793, Dalton left for the Manchester to teach mathematics, physics, and chemistry in a college. He spent most of his life then there teaching and researching. In 1808, he presented his atomic theory, which was a turning point of the study of matter. According to the Dalton's atomic theory, all matter, whether an element, a compound, or a mixture, is composed of small particles called atoms. The postulates of the theory may be states as like this. First, all matter are made up of very tiny particles called atoms. Second, atoms are indivisible, which are cannot be created or destroyed in a chemical reaction. Third, atoms of a given element are identical in mass and chemical properties. Fourth, atoms of different elements have different masses and chemical properties. Fifth, atoms combine in the ratio of small whole numbers to form compounds. Sixth, the relative number and the kind of atoms are constant in given compound. You will study in the next video of the another topic that all matter are made up of still smaller particle. Then after, let us see what is an atom. Have you ever observed a mason building wall? From this wall a room and then a collection of rooms to form a building. What is the building block of the huge building? What about the building block of an ant hill? It is a small grain of sand. Similarly, the building block of all matter are atoms. How big are atoms? Atoms are very small. Uh, they are smaller than anything that we can imagine or compare with. More than million of atoms, when stacked with, make a layer of barely as thick as this sheet of paper. The radius of circle is measured in nanometer. The 1 upon 10 raised to the power 9 meter equals to 1 nanometer. 1 meter equals to 10 raised to the power 9 nanometer. Let us see relative size and the radii of the some atoms. First, atom of hydrogen, the radii of the atom of hydrogen in meter is 10 raised to the power negative 10. And then after, the molecule of water have the 10 raised to the power negative 9 meter radii. The molecule of hemoglobin is 10 raised to the power negative 8 meter radius. Grain of sand have the radius of 10 raised to the power negative 4 and is 10 raised to the power negative 2. And then after, the watermelon radius is the atom of the watermelon is the 10 raised to the power negative 1 meter. We might think that if atoms are so insignificant in size, why should we care about them? This is because our entire world is made up of atoms. We may not be able to see them, but they are there and constantly affecting whatever we do. Through the modern techniques, we can now produce the magnifying techniques. We can now produce magnified images of the surface of elements showing atom. Let us see the image of surface of silicon. You can able to see the image of surface of silicon on your screen. Then after, we will start the another topic, that is what are the modern day symbols of the atoms of different elements. Let's start this topic. Dalton was the first scientist to use the symbol for the element in a very specific sense. When he used a symbol of an element, he also meant the definite quantity of that element, that is one atom of that element. Berzelius suggested that the symbols of element he made from one or two letters of the name of the element. There are symbols of some elements as proposed by Dalton on your screen. Then after, in the beginning, the names of the elements were derived from the names of the place where they were found the first time. For example, the copper was taken from Cyprus. Some names were taken from specific color. For example, gold was taken from the English word the meaning yellow. Now a day IUPAC international, the full form of the IUPAC is International Union of Pure and Applied Chemistry, approved the names of element. Many of the symbols are the first on or one or two letters of elements. Now in the English, the first letter of the symbol is always the written in the capital letter or in the uppercase, and the second letter is always in the lowercase, which we known as the small letter. For example, the hydrogen have the uppercase letter H, and the second aluminium Al, and not Al, which those are capital in the symbol of aluminium. The first letter have uppercase and the second is lowercase. Symbol of the some element are formed from the first letter of the name and a later appearing letter in the names. Examples are first fluorine, that is Cl. C is a uppercase letter and the L is a lowercase letter. And the second example is the zinc. In the zinc, Z is a capital letter and N is a small letter. And there are some many more examples for this. Other symbols have been taken from the names of elements in Latin, German, or Greek. For example, the symbol of iron is Fe from its Latin name ferrum. Sodium is Na from the natrium. Potassium is K from the kalium. Therefore, each element has a name and a unique chemical symbol. So that let us start the another topic, that is the atomic mass. The most remarkable concept of the Dalton's atomic theory proposed what was the most remarkable concept of Dalton's atomic theory proposed was that of the atomic mass. According to him, each element had the characteristic atomic mass. The theory could explain the law of constant proportion so well. The scientists were promoted to measure the atomic mass of an element, since determining the mass of an individual atom was a relatively difficult task. Relatively, atom masses were determined using the laws of chemical combination and the compounds formed. Let us take an example of a compound, carbon monoxide. The symbol of carbon monoxide is CO, formed by the carbon and oxygen. It was observed experimentally that 3 grams of carbon combines with the 4 grams of oxygen to from CO. In other words, carbon combined with 4 upon 3 times of its mass of oxygen. Suppose we define the atomic mass unit earlier abbreviated as AMU, but according to the latest IUPAC, you know that the full form of IUPAC recommendations, it is now written as U. The U is for undefined mass. If you don't know the full form of IUPAC, I remember you the full form of the IUPAC is International Union of Pure and Applied Chemistry, as equal to the mass of one carbon atom. Then we would assign a carbon an atomic mass of 1.0 U and the oxygen an atomic mass of 1.33 U. However, it is more convenient to have these numbers as a whole number or as near to a whole number as possible. While searching for various atomic mass units, scientists initially took 1 upon 16th of the mass of the atom naturally occurring oxygen as the unit. This was considered relevant due to the two reasons. First reason is that oxygen reacted with the large number of elements and formed compound. This atomic mass unit gave masses of atomic this atomic mass unit have masses of most of the element as whole number. However, in 1961, for a universally accepted atomic mass unit, carbon-12 isotopes was chosen as the standard reference for the measuring atomic masses. One atomic mass unit is mass unit equal to exactly 1/12 of the mass of one atom of carbon 12. The relative atomic mass of all elements have been found with respective of atom of carbon 12. Imagine a fruit seller selling fruits without any standard weight with him. He takes a watermelon and says this has mass equal to 12 units. It means 12 watermelon units or the 12 fruits mass units. He makes 12 equal pieces of the watermelon and finds the mass of each fruit he is selling. relative to the mass of one piece of watermelon. Now he sells his fruit by relative fruit mass FMU, as in shown on your screen. Similarly, the relative atomic mass of the atom of an element is defined as the average mass of the atom as compared to 1/12 of the mass of the carbon 12 atom. Let us see the atomic mass of a few elements. The mass of hydrogen element is 1, the mass of carbon is 12, the mass of nitrogen is 14, oxygen is 16, sodium is 23, magnesium is 24, sulfur is 32, chlorine is 35.5, calcium is 40. Then after, let's start the another topic, that is how do atoms exist. Atom of the most elements are not be able to exist independently. Atoms form molecules and ions. These molecules or ions aggregate in large number to form the matter that we can see, feel or touch. Then after, the one question arises in your mind, that is what is a molecule. A molecule is in general a group of two or more atoms that are chemically bonded together, that is tightly held together by the attractive force. A molecule can be defined as the smallest particle of an element or a compound that is capable of an independent existence and shows all properties of that substance. Atoms of the same element or the different elements can join together to form the molecules. Then after, let us see the molecules of elements. The molecules of an elements are constituted by the same type of atom. Molecules of many elements such as argon, helium, etc. are made up of only one atom of that element, but this is not the case with most of the non-metal. For example, a molecule of oxygen consists of two atoms of oxygen, and hence it is known as the diatomic molecules. O2. If atom of oxygen unit into a molecule instead of a usual two, we get ozone. The number of atom constituting a molecule is known as its atomicity. Metal and some other elements such as carbon do not have the simple structure but consist of very large and indefinite number of atoms bonded together. Let us look at the atomicity of some non-metals. The atomicity of some non-metals are shown on your screen. Let's read it. The type of element is non-metal. The name of element argon. The atomicity of argon is monoatomic. The atomicity of helium is monoatomic. Oxygen is diatomic. Hydrogen is also diatomic. Nitrogen is diatomic, and chlorine also diatomic. And then after, the another element is phosphorus. The atomicity of phosphorus is tetraatomic. And the last, the sulfur. The atomicity of sulfur is polyatomic. Molecules of compounds. This is the another topic. Let's start this topic. Atoms of different elements join together in the definite proportion to form molecules of the compound. Few examples are given in the table, which is shown on your screen. The table represents that the compounds, that is water, combine the elements hydrogen and element ratio by mass of this compound is 1:8. Ammonia is a compound which is combining element from the nitrogen and hydrogen. The ratio by the mass of the compound ammonia 14:3. And the another compound is carbon dioxide. The combining element is carbon and oxygen. The ratio by mass is 3:8. Then after, let us move on the another topic, that is what is an ion. Compounds composed of metal and non-metal contains charged species. The charged species are known as ions. An ion is charged particle and can be negatively or positively charged. A negatively charged ion is called an anion, and the positively charged ion is cations. For the example, sodium chloride, NaCl, its constituents particles are positively charged sodium ions and negatively charged chloride ions. Cl negative ion may consist of the single charged atom or a group of atoms that have a net charge on them. A group of atoms carrying charge is known as polyatomic ion. We shall learn more about the formation of the ion in the another chapter of the chemistry. Let us see the one table to understand the ionic compound. The ionic compound is calcium oxide. The constituting element is calcium and oxygen, and the ratio by mass is 5:3. The second is magnesium sulfide. The constituting element is magnesium and sulfur. The ratio by mass is 3:4. And then after, third is sodium chloride. Sodium and chloride is a constituting element of the sodium chloride. The ratio by mass is 23 is to 35.5. Then after let us move on the another topic, that is writing of chemical formulae. The chemical formula of compound is a symbolic representation of its composition. The chemical formula of different compounds can be easily written easily. For this exercise, we need to learn more symbols and combining capacity of the element. The combining power or the capacity of an element is known as valency. Valency can be used to find out how the atom of an element will be combined with atoms of another element to form the chemical compound. The valency of the atom of an element can be thought of as hands on arms of that atom. Human being have two arms and an octopus have eight. If one octopus has to catch hold to five people in such a manner that all the eight arms of the octopus and the both arm of the all humans are locked, how many humans do you think that the octopus can hold? Represent the octopus with O and human with H. Can you write a formula for this combination? Do you get OH4 as the formula? The subscript 4 indicates the number of humans held by the octopus. The valency of the some common ions is given in the table which is shown on your screen. We will learn more about the valency in the next chapter. The next chapter we will see in next audio of the KHC's audio. Then let's see the table. The valency 1 have sodium, potassium, silver and copper 1. The symbol of sodium is Na plus, potassium is K plus, silver is Ag plus, copper is Cu plus. You can able to study the whole table on your own. Therefore, we skip this table and move on the another topic. The rule, another topic is the rule of that you have to follow while writing the chemical formula as follows. First, the valency or charge on the ion must balance. The second is when a compound consists of of metal and a non-metal, the name or symbol of the element is written first. For example, the calcium oxide CaO, sodium chloride NaCl, iron sulfate FeS, copper oxide CuO, etc., where oxygen, chlorine, sulfur are non-metal and are written on the right, whereas calcium, sodium, iron and copper are metals and are written on the left. And the third is the in compounds from the polyatomic ions, the ions is enclosed in a bracket before the writing. The numbers of the indicate the ratio. In case the numbers of polyatomic ion is 1, the bracket is not required. For example, NaOH. And then after, let's study another topic, that is the formula of a simple compounds. The simplest compounds, which are made up of two different elements, are called binary compounds. Valency of the some ions are given in table that we are seeing the previous topic. We will see the that table on your screen, and I'm also tell that the you can able to see this table. In this table you can use this to write a formula for compound. By writing the chemical formula for compound, we write the constituent element and their valency as shown below. Then we must cross over the valency of the combining atoms. Let us see the example. The first example is formula of hydrogen chloride. The symbol of hydrogen is H and chloride is Cl. The valency of hydrogen is 1, chloride is 1. If we change the number of the valency, then H comes in the under of 1 comes in under of H, and and the valency of H which comes in under of Cl. The formula of compound would be HCl. The another example we will show on your screen. You can study this example, and if any doubt, then type in comment box, and we wait for you can able to read these pictures for read. Okay, the time is over. Let us start the another topic, the molecular mass and the mole concept. The first we will study the molecular mass in this topic we will discuss the concept of the atomic mass. The concept can be extended to calculate the molecular mass. The molecular mass of the substance is the sum of the atomic masses of all atoms in a molecule of the substance. It is therefore a relative mass of a molecule expressed in an atomic mass unit, that is U. Let us calculate the relative molecular mass of the H2O. And the another question is calculate the molecular mass of the HNO3. Firstly, we will solve the first question, that is to calculate the relative molecular mass of the water. That the formula of water is H2O. The atomic mass of the hydrogen is 1U. The oxygen and the oxygen have 16U. So the molecular mass of the water, which contain 2 atoms of the hydrogen and 1 atoms of the oxygen, is 2 into 1 plus 1 multiplied by 16, that is 18U. And the another question is the molecular mass of the HNO3 equals to the atomic mass of H plus the atomic mass of the N plus 3 into the atomic mass of O. This is equals to 1 plus 14 plus 48 equals to 63U. Let us see the formula unit of mass. The formula unit of mass of a substance is the sum of the atomic mass of all elements in the formula unit of a compound. Formula unit of mass is calculated in the same manner as we calculate the molecular mass. Only difference is that we use the word formula unit for the substances which constituent particle or ion. For example, sodium chloride are discussed above has the formula unit NaCl. It is the formula unit. Mass can be calculated as 1 into 23 plus 1 equal multiply by 35.5 is equals to 58.5. We will see the mole concept. Let us take an example of the reaction of the hydrogen and oxygen to form water. 2H2 plus O2, it gives the 2H2O. The above reaction indicates that the 2 molecules of the hydrogen combine with the 1 molecules of the oxygen to form 2 molecules of water, or the 4U of hydrogen molecule combined with 32U of oxygen molecules to form the 36U of water molecule. We can infer from the above equation that the quantity of substance can be characterized by its mass or the number of molecules, but a chemical reaction equation indicates directly the number of the atom or molecule taking part in the reaction. Therefore, it is more convenient to refer to the quantity of a substance in terms of the number of its molecule or atom rather than their mass. So a new until mole was introduced. 1 mole of any piece atoms, it means atoms, molecules, ions or particles. Then then 1 mole of any piece is that quantity in number having a mass equal to its atomic or molecular mass in grams. The number of particles present in 1 mole of substance is fixed with the value of 6.022 into 10 to the power 23. This is the experimentally obtained value. The number is called the Avogadro Constant or the Avogadro number, which is represented by n, in which the under 0 named in honor of the Italian scientist Amedeo Avogadro, of 1 mole of everything is equals to the 6.022 into 10 to the power 23 in number, as 1 dozen equals to 12 knots and 1 gross is equals to 144 knots. Besides being related to the number of a mole, has one more advantage over a dozen or a gross. This advantage is the mass of mole of a particular substance is fixed. The mass of 1 mole of the substance is equals to the relative atomic or the molecular mass in the gram. The atomic mass of the element gives us the mass of one atom of that element in the atomic mass unit. That is, you to get the mass of the 1 mole of atom of that element, that is molar mass. We have to take the some numerals value but change the unit of from U to G. Molar mass of the atoms is also known as the gram. Atomic mass of the atom is known as the gram atomic mass. Sorry, this sentence is repeated. For example, atomic mass of the hydrogen is equals to 1U. So gram atomic mass of the hydrogen is 1 gram. 1 U hydrogen has only one atom of hydrogen, 1 gram of hydrogen has 1 mole atoms, that is 6.022 into 10 to the power 23 atoms of hydrogen. Similarly, 16 U oxygen has only one atom of oxygen, 16 G oxygen has 1 mole atoms, that is 6.022 into 10 to the power 23 atoms of oxygen. To find the gram molecular mass or the molar mass of the molecule, we keep the numerical value of the same as the molecular mass, but simply change units as above near from U to G. For example, as we have already calculated molar mass of the water H2O is 18 U. From here we understand that 18 U of water has only one molecule of water. 8 G water has only one mole molecules of water. Consists need the number of atoms, and for this they need to relate this mass in grams to the numbers. It is done as follows: 1 mole is equals to the 6.022 into 10 to the power 23 numbers is equals to the relative mass in gram. Thus a mole is the chemist's counting unit. The word mole was introduced around the 1896 by the William Ostwald, who derived the heap and pile. A substance may be considered a heap of atoms or molecules. The unit mole was accepted in 1967 to provide a simple way of reporting a large number. The massive heap of atoms and molecule in a sample, which we can see in the next video, or you can able to see in your textbook of the 9th standard, which have the page number 41. At that point we end the video because the video is very long, and I hope you are also bored from this video because this video is very long. You can rest and we will meet in the next video. In the next video we will study the summary of this chapter. Thanks for watching.